Hey people, let's start learning for earning.
The word robot entered the human vocabulary through a 1921 Czechoslovakian play. It was derived from the word robota, which translates simply to forced labor. 2 decades later, the Russian-American author Isaac Asimov took that concept further, officially coining the term robotics in his 1942 science fiction story, Runaround. But engineering doesn't run on fiction. It requires exact mathematical boundaries to turn abstract ideas into physical reality. By tracking the mechanics of these machines, from the heavy, fixed steel arms of the early 20th century to the fluid, soft bodies being printed in labs today, we can see a clear evolutionary line driven entirely by 3D physical geometry. To trace that line, we start at the absolute baseline of automation, the industrial robot. The International Organization for Standardization defines this baseline in ISO 8373. It requires an industrial robot to be an automatically controlled, reprogrammable, multi-purpose manipulator. In this context, reprogrammable means the machine's programmed motions can be changed strictly through software, without requiring physical alteration to the hardware itself. Multi-purpose means the same hardware adapts to different applications, usually by physically swapping the tool at the end of the arm. And finally, the ISO mandates that this manipulator must be programmable in 3 or more independent axes of motion. Grasping the strict, rigid mathematics of this factory standard is mandatory. If we want to understand how modern machines walk through forests or safely handle human tissue, we first have to understand how they are built from the ground up. Physically, every robot is constructed as a kinematic chain. This chain is assembled from individual rigid bodies, which engineers call links. Those links are bolted together by joints. And these joints are driven by actuators, typically electric or hydraulic motors, that act as the muscles of the machine, delivering force to create motion. The most widely used joints operate with a single degree of freedom. The first of these is the revolute joint. As shown in this 3D model, a revolute joint allows for pure rotation about a single central axis, functioning much like a hinge. The second primary single degree of freedom connection is the prismatic joint. Instead of rotating, the prismatic joint allows for pure translation. It slides straight back and forth in the exact direction of the joint axis. When you connect multiple links and joints, you create a configuration space, or C-space. This is a mathematical specification of the exact location of all points on the robot at any given moment. The dimension of that C-space is determined by the robot's degrees of freedom. This is the precise number of independent parameters required to specify the robot's configuration in 3-dimensional space. Every motion on a factory floor, no matter how intricate the welding or assembly task appears, is calculated by mathematically combining these fundamental prismatic, sliding, and revolute twisting joints. This photograph shows a Cartesian, or gantry configuration. It is built entirely from 3 prismatic joints that align perfectly with the X, Y, and Z axes of a standard coordinate system. Because this overhead structure is highly rigid, it excels at high-stiffness tasks like heavy lifting, precision machining, and water jet cutting. This diagram illustrates a cylindrical arm configuration. By combining one revolute joint at the base with 2 prismatic joints, it maps out a cylindrical work envelope. The horizontal sliding axis makes it ideal for reaching straight into horizontal cavities. Swapping one of those prismatic joints for a second revolute joint yields a spherical configuration, carving out a hollow sphere of reach. Next is the SCARA configuration, which stands for Selectively Compliant Assembly Robot Arm. SCARA utilizes 2 parallel revolute joints. This specific geometry provides high vertical stiffness for pressing parts downward, while allowing slight horizontal compliance to align components, making it the dominant standard for high-speed electronics assembly. Finally, this diagram on the bottom right isolates the anthropomorphic, or articulated geometry. It uses 3 revolute joints designed to directly mimic the human shoulder, elbow, and wrist. Because all joints rotate, it offers the highest level of manual dexterity. This flexibility makes the anthropomorphic arm the most common industrial design, accounting for roughly 59% of global installations. These configurations conquer precise 3D workspaces efficiently, but their rigid accuracy is entirely dependent on staying bolted to a fixed base in a highly structured factory environment. Advanced mobile robots break that limitation by detaching from the floor entirely. This detachment forces an immediate shift in engineering priorities. The primary challenge moves away from spatial manipulation and toward autonomous locomotion. The first tier of this mobility is achieved through wheeled platforms. Autonomous guided vehicles, or AGVs, rely on wheel encoders and external sensors to navigate. They excel in relatively flat, controlled terrains like warehouse floors or hospital corridors. When the terrain becomes entirely unstructured and uneven, wheels fail. The solution requires legged platforms. Engineers look to biomechanics to solve this, studying and replicating the exact locomotion strategies of living organisms, ranging from bipedal humanoids to hexapod insects. Controlling these legged machines is vastly more difficult than operating a fixed arm. The robot must perform continuous, dynamic stability calculations in real time, adjusting dozens of joints simultaneously just to keep from falling over. Once that stability is achieved, these platforms can be deployed as field robots to navigate agricultural rows, or as service robots clearing debris in disaster zones. Yet, even with advanced mobility and AI, building a robot from rigid metal links remains a severe liability when the machine must safely interact with a delicate marine ecosystem or maneuver inside the human body. This composite breakdown illustrates a radical departure in engineering: soft robotics. This subfield abandons rigid links entirely in favor of highly compliant, flexible materials. Replacing metal and ceramic with soft resins drastically lowers the machine's mechanical impedance. When a soft robot makes contact with a human, the material absorbs the force, making close-quarters interaction inherently safe. Standard electric motors can't drive these flexible bodies. Instead, soft actuation draws direct inspiration from biological mechanisms, like the osmotic potential that allows plant cells to swell and shift. As this fluid dynamics animation demonstrates, soft robots utilize fluid or pneumatic flow moving inside semi-permeable membranes. The controlled transport of that fluid generates internal pressure differentials, which forces the compliant material to change its volume and bend into targeted shapes. This creates a massive control problem. A rigid arm has a fixed number of joints. A continuously bending piece of silicone effectively has infinite degrees of freedom. The standard mathematics developed for rigid bodies fail completely here. To manage this, engineers must rely on automated design tools, like evolutionary algorithms, to simultaneously calculate and optimize the robot's shape, material properties, and controller for a specific task. Fabrication requires a similar reinvention. Conventional subtractive manufacturing techniques, like drilling or milling, are useless on complex, highly deformable bodies. Looking at this 3D printed, octopus-inspired model, we see the primary alternative: advanced additive manufacturing, such as multi-material robocasting. These specialized printers lay down silicone inks or shape memory polymers. The resulting structures automatically bend, twist, or contract when exposed to heat, water, or light. Soft robotics forces engineers to sacrifice the perfect mathematical predictability of rigid arms, trading it for the ultimate adaptability of biological forms. The entire history of automation is an ongoing effort to manipulate physical materials to conquer three-dimensional space. It began in the factory, mapping perfect mathematical configurations onto rigid metal joints to achieve maximum repetition and industrial precision. It advanced by detaching the base, integrating complex sensors to allow wheeled and legged machines to stabilize themselves across unstructured terrain. And it is currently evolving by discarding the rigid link entirely, engineering compliant, fluid-driven bodies that survive chaos by adapting to it. The capability of modern machines is not the result of science fiction. It is the result of physical geometry, continuously evolving to meet the demands of the real world.
Let's study more and like, share and subscribe for such more content, and comment something you want to learn.